Hello everyone, I'm Janki Bhimani, Assistant Professor and Director of Data Management Research Lab at FIU. Today I'm going to discuss our research on fine-grained control of concurrency within KV-SSDs done in collaboration with Samsung Semiconductors and Northeastern University. So let's get started. The rate at which we are increasing the amount of data each day, I think the term big data might soon have to be renamed as humongous data. But this growing data leads an important question in front of us, which is how can we accelerate data intensive applications, ensuring that we are taking best possible advantage of emerging technologies such as KV-SSDs. First, I'm going to give a brief background and discuss what motivated this work. Then I'm going to discuss the KV-SiPs framework and infrastructure itself, followed by its evaluation, and finally conclude. So as we see in this figure, the comparison of block SSD IO stack and a KV IO stack, we see on the right, the KV IO stack is capable of storing unstructured objects directly into the storage device, bypassing some of the intermediate system layers such as file system, block layer. Now we see at the bottom for the block SSD, the data is stored within fixed size blocks, each of which consist of fixed size pages. But for KV SSD, the data can be stored directly as variable sized key value pairs. So some of the research questions that triggers this project or this work are, do we need SSDs to be block-based devices? Can we achieve better performance without intermediate data conversion layers? Can KV-SSDs improve performance of multi-threaded file-based applications as well? Towards answering these questions, we innovate a new infrastructure called KV-SiPs for fine-grained control of concurrency within KV-SSDs. So currently, the KV-SSDs are capable of performing key value operations such as store, retrieve, delete, etc. They cannot manage the critical operations such as shared memory buffer management, which is required to process or execute any multi-threaded parallel application. They are also not capable of managing the thread safety, and originally block layer is in charge of managing thread safety, especially by performing asynchronous IOs. But now in KV-SSDs, we neither have file system nor have block layer. So the current KV-SSDs cannot support running parallel multi-threaded file-based applications on itself, and that's what motivated this work. So the major contribution of our work are, we develop an infrastructure to execute workloads with parallel data threads, along with the traditional parallel compute threads. We design a controller which decides optimal number of parallel data and compute threads that results in better resource utilization. We designed key value concurrency manager to maintain memory mapping and thread safety while executing parallel workloads with parallel compute as well as parallel data threads. We develop different processing modules such as sequential parallel compute, PC, and parallel data access along with parallel compute, PDA plus PC, in order to compare the performance of our stack KV-SiPs with the traditional block SSD stack. We use the same hardware, which is Samsung PM983 KV device, Samsung PM983 storage device SSD, with the KV infrastructure and the block infrastructure. So same hardware with different driver, different IO stack with the same application. We evaluate both the stacks hand in hand. So let's see what motivated this work. These are snapshots of some of the results that actually got us thinking in this research direction. First on the left, we see that the throughput, which is higher the better y-axis, KV-SSD is able to achieve higher throughput both for reads and writes or get and put operations when compared to file-based operations on a block device. On the right-hand side, we see that when we increase number of parallel compute threads, as we expect, the y-axis is runtime, so lower the better, as we expect, compared to sequential runtime with more number of parallel compute threads, we are able to reduce the runtime. But eventually with around 180 to 120 parallel compute threads, the performance saturates. But upon developing an infrastructure that allows us to support parallel data threads within the storage device, along with the parallel compute threads, we saw that there is a scope of further reduction in runtime or further performance improvement, as we see on the graph cluster in the red checks box towards the right. So two main takeaways motivated this research. First, lightweight KV stack of KV-SSD yields better throughput. Second, multiple data access threads launched by each compute thread can further reduce the runtime. Jumping into the KV-SIPs framework, our framework mainly consists of two components, compute path and the data path. Compute path has a lightweight wrapper to translate file-based application to key-value-based workload by using simplistic functions such as KV-create and KV-map. But the main contribution of compute path is how to launch multiple compute threads as well as how to launch multiple data threads from each compute threads. Now, when I say how to launch, that automatically would have got you thinking that, okay, how do you decide how many compute threads should you launch or how many data threads should be launched? That's exactly the controller we designed in compute path is responsible to perform the task. Then in the data path, once the compute threads and data threads are launched, data path is responsible to ensure that the execution of workload with this degree of parallelism happens in a correct way. So we designed multiple submission and completion IOQs and its management framework to ensure correct memory mapping of user queues as well as the thread safe asynchronous key value IO operations within the KV device, ensuring that everything works in parallel as we expect. But along with parallelism, we also ensure that we get the data actually what we want, or we are able to write the data that we want to write on the device. Going a bit deeper into our design and its key components, we have three main components in our design. First, we modified OpenMP library functions to control the launch of parallel compute and parallel data threads. Here, because this is a real implementation, we chose OpenMP multi-threading library, but the same concept can be used with any other multi-threading library such as pthreads as well. Second, our controller decides number of optimal parallel compute and parallel data threads. In order to do that, we design two different components or two different methods. First is KV-ins, which is a brute force periodic instrumentation method. We instrument CPU utilization, throughput, and memory utilization. So first we observe the CPU utilization until either it saturates, we keep increasing number of parallel compute threads, or until we are out of number of parallel compute threads supported by number of cores in that machine. Then in parallel, we also keep a track of application throughput as well as memory utilization. So we keep increasing number of parallel data threads launched by each parallel compute thread until either the memory utilization saturates or if we see a drop in throughput upon further increasing parallel data threads. So it's a runtime process, and we figure out number of parallel compute threads, parallel data threads, configure that in the system, and run the workload with that. KV mod is more of like an offline modeling process. So for compute intensive workload, as instrumentation is a big overhead, so KV-ins is not a good method for compute intensive workload, for which we design KV mod, where we simulate the parallel thread and the processing infrastructure with MMC queuing theory. I wouldn't go much in depth about the details and the objective function of our simulation model. Please refer to our paper with that. But to briefly describe, we model each parallel data thread and compute thread with parallel servers. So the processing service rate of each of the server captures the throughput of the overall workload. We also use functions like erlang-c to capture if the job can immediately be served or it needs to wait in the queue for a while. Eventually, the objective is to find out optimal number of parallel servers, which represents optimal number of parallel threads. So from the simulation model, we calibrate the simulation model with respect to real system. We find or we predict the optimal number of threads, and then we run the real workload on the real system using this predicted number of threads. Finally, in order to ensure that everything runs correctly and still in parallel, we modify some of the functions such as KVSStore, KVSRetrieve to perform correct memory buffer allocations. So we introduce the functionality of memory buffer allocations, and we manage an additional bitmap to log key to the OpenMP thread ID and corresponding IO submission queue track. So every time we perform any operation on different IO submission queues, this log helps us to keep a track of all the operations and ensure the correct completion of each issued operation in an asynchronous manner. Thus, the capability to execute workload with multiple parallel data threads, along with traditional parallel compute threads, that allows us to improve overall throughput of application, utilizing maximum possible storage bandwidth. We integrate OpenMP pragmas, which are compiler directives, with key value Linux KDD to maintain memory mapping and thread safety when running a multi-threaded application on KV-SSD. We design different processing modules as this is real implementation. So each of these processing modules were implemented for both block stack as well as the KV stack to compare, to have a fair comparison of both. In each of our processing modules, especially in the right-hand side one, the most exhaustive parallelism one that has parallel compute threads as well as parallel data threads launched from each compute thread, we particularly ensure that we avoid data race conditions and we take appropriate measures at application level, operating system level, as well as the key value device driver layer. So to read about more details on what measures we take, please refer to our paper. Let's have a brief glance at the evaluation and how does this KV-SiPs performance behave. So as an overview of the storage-related system configuration, we use Mission Peak node that has very huge amount of memory, but here we are evaluating storage performance, so we limit the system memory to 100 GB. We use Samsung PM983 SSD, both with block infrastructure as well as the KV infrastructure, and the file system and the block size that we use for the block infrastructure. So looking at the performance overview, first, in this figure, we see that we are comparing the bandwidth of performing get or reads or performing put or writes while using file-based block infrastructure, block device, and key value-based key value device. We see that on x-axis, when we increase number of threads, the bandwidth increases as we expect. But while we are using the block device, which is the blue bar, we see that we are nowhere near to the reported bandwidth, or we are nowhere near to saturating the available bandwidth of the device, which is shown by the green dotted line on the top. This is the available bandwidth taken from the data sheet of the device. But with the KV device, with higher number of threads, we are able to saturate the bandwidth. So that's for good. And we see the consistent behavior for both get and put as well. Thus, KV-SSD can saturate the available device bandwidth and scale better upon increasing number of parallel data threads due to its lean I/O stack. KV-SiPs can obtain speedup of 2x while performing load and store compared to block SSD. What's the evidence of the performance gain that we observed in the previous slide? So here I'm showing on y-axis normalized mean time spent on the locks. This is one of the places we observed that KV-SiPs is able to perform much better or save much time compared to the block infrastructure. So the time spent waiting for locks within the adapter queues, submission queue, as well as the completion queue of Linux kernel is shown in the bar. Time lower the better because this is an overhead. So when we compare block with KV ins and KV mode, which both are operated on KV device, we see that we are able to save around 35% of time. The bottleneck between adapter queue and the device queue is reduced with KV-SiPs to be able to better utilize the available 64K queues in NVMe controller. Now, let's look at resource utilization. So here we compare the throughput on the left-hand side of y-axis, and the right-hand side y-axis is the memory consumed. The memory cap of the system is 100 GB. So the orange line shows the memory consumed at runtime, and the blue dot shows the throughput of the application. This experiment was conducted for a long duration. By long, I mean couple of days. As you observe the x-axis, that's the time in hours. So 24 hours makes one day, right? So definitely a couple of days with 100 hours. We see that when we ran application initially for the block device, that's the plot A on the left, Application was doing pretty good. The throughput was fine, and we observed it for almost a day. But the next day, by the night, we saw that the throughput dropped, kept dropping as we proceeded, and around second day, we observed that the throughput is almost negligible, and that's the point when the trashing began. So the memory was almost saturated, and there was very less, minimal amount of productive work that was done. While for the KV device, that's a graph on the right-hand side, we see that this problem didn't happen. The throughput was pretty good, and it sustained for whole that duration of couple of days, while the increase in memory utilization was very gradual compared to what we saw on the block device. This why this thrashing does not happen on KV-SiPs. That's because KV-SiPs enables an application to fetch the required data into memory by each parallel thread, unlike block caching. It saves the memory space and conserves CPU cycles for fetching and then later evicting unnecessary data. KV-SiPs can thus better utilize the same amount of resource, memory and CPU to further accelerate an application with larger workload. Thus, to conclude, we developed this KV-SiPs infrastructure that enables executing multiple parallel data threads along with parallel compute threads. This allows us to fine-grain control over the interactions between parallel compute and parallel data threads to improve overall system concurrency. As well as in order to show the proof of concept, we implemented it into a real system, modifying the operating system as well as the system layers to integrate OpenMP Pragma with key-value Linux kernel device driver protocols in order to achieve thread-safe data-level parallelism. Thank you.
So thank you very much, Janki. That was a nice talk. And I believe you are here to answer the questions as well.
Hi, thank you.
Hi. So while we are waiting for questions, so let me start with, so I have a high-level question. In one of the earlier slides, you mentioned about the goal to understand if we need SSDs to be block-based devices at all, or key-value interfaces suffice. And the paper answers this question to some extent. And I was wondering how your observations would change, say, in the future, when we have block-based devices with better bandwidth than the current class of devices.
Yeah, so from what we observed or what we learned in this project was that the block-based infrastructure, now we do have devices that supports really high bandwidth, but the problem is that we are not able to saturate that because of the overhead that's caused by the software stack itself. And that's why even in the previous talk, or even in the last year's SYSTOR work on KV-SSD, the KV-SSD work in fast, we see that for KV stores, KV-SSDs perform very good. So in this work, we started thinking in an orthogonal way that the reason behind why KV devices are performing good is because we are able to avoid the software stack. Now, is there a way that we can run a normal file-based application avoiding this stack? There are many challenges. I would say that this work is a very preliminary work in this direction. We do evaluate the correctness because we want to ensure that we get the output. Let's say, for example, if we are running matrix multiplication, the output is correct. But then there could be many other issues because of the concurrency, as we saw in today's keynote in the morning. We still don't enter that arena yet. It's a very preliminary work with a lot of assumption. If we have complex real-time applications, there might be many shortcomings or bottlenecks. So we might have to introduce or reintroduce the system level operations back again. And that would again make the overhead same. So I think it's still yet to explore in that direction, but it's interesting to kind of dig more in this.
Okay, great. So we hope to have more papers on this topic then in the future. So any more questions on this talk? So let me ask one more question. So this long-running experiment you had, I think it was for resource utilization, that was quite exciting. I had questions about the thread configurations for this long-running experiment. Was the thread configuration constant across the entire experiment? Or do you have data for what was the actual number of data and compute threads for this experiment? And how sensitive, it's possible that this particular experiment does well because you have the right set of data and compute threads. But if you increase or decrease that number by a small margin, the numbers suddenly become worse because that's like the perfect point. So do you have a notion of how sensitive your system is to the number of threads?
That experiment that I show in slide, that's run. So we, as I introduced in the earlier slide, the KV-ins and KV-mode, those two ways to run application, both of them, they decide number of compute threads and number of data threads at runtime. And we deploy this for both block infrastructure as well as the KV infrastructure. So the resource utilization is running in KV-ins mode in the graph that I showed. And that's why it just determines the number of optimal threads at runtime. So we don't pre-configure that.
Okay. And do you have a ballpark sense of what was the number of range of threads that was used in the experiment?
We found that the number of data threads, that's like number of data threads launched by each compute thread, that's usually a singular digit. The optimal number saturates the singular digit, at least for the applications that we ran until now. There are many things, as I said, yet to explore in this arena. But the number of compute threads, depending, that would mainly depend on the number of cores that the node has. So if let's say if we have around 98 cores in our node, then it's saturated around like 10 less than that, around that. Because the remaining core, like the remaining compute power is being used by other system operations at that time.
Okay, yeah. So that makes sense. So yeah, thank you, Janki, for the presentation and for answering questions.